today is about navigation more than the other previous times being a bit more about memory. So this work is titled multi-agent navigation and a social place cell hypothesis. There should be the word cell in there, I guess. And this is jointly done with Robert Tang, who's in China. He's a collaborator of mine. And this is kind of mostly based on this archive paper, if you're interested in looking at that. And then we also did like a workshop presentation, which is about the latter half of the talk. I should also mention that this talk is going to start from a more sort of abstract mathematical perspective and then trend towards a neuroscientific interpretation. So it's a bit of the reverse as to like that order that I think in the past I've maybe started more towards the neuroscience side and then gone towards more how can we bring some math into this, but now it's the opposite. Okay, so first I want to ask, do you think that an autonomous vehicle could navigate this intersection? This is a recording from an intersection in Bangladesh with lots of mopeds and even those two very brave individuals, I think, in the middle of the intersection walking through it.
To answer your question,
I personally,
is the autonomous car allowed
yes.
to crush the drivers?
Okay, yeah, that I suppose is a technical solution to moving through the intersection. So I wouldn't consider that safe navigation. So no, I will ban killing of humans in my definition of can something navigate. So I mean I think the answer pretty obviously is that our current technologies aren't able to do this. And I suppose a question is how could we, if we wanted, to democratize and have these technologies available in different situations at different places, then we might need to make technologies work in this sort of context as well. And another question I have is, well, how can we more deeply understand multi-agent navigation mathematically and just scientifically? This is a recording of birds, so each of those black dots is a different bird, and this particular phenomenon happens quite a lot in different species, but this one in particular I think is with sparlings, and it's called a murmuration, and it's a beautiful undulating pattern. Kind of schools of fish do similar things as well, and you can look at this and be mesmerized for quite a while, at least I can. And people from the statistical physics community will say, okay, well, we sort of know already how these things work. We just have some local rules for each individual, and then they kind of interact in these magical ways to give these magical phenomena. And I say, yes, that's true, but I want to know more about it. So one way to do that is to, rather than taking the statistical physics approach, take a little bit more of just to take a different approach. And one approach is to use some geometric group theory, which we're going to talk about today. So rather than take a real world example with 3 dimensions of space and time and one of time, we're just going to take a really boring, well, not boring, but at least it's a simple perspective to begin with in Gridworlds. So Gridworlds are these 2-dimensional flat arrays of cells where you arrange the square cells as into these grids, and in our case the cells can be occupied or not, either by a koala or a beach ball, and these are empty cells here. This whole thing is a 3x3 grid world. Now, you might say, okay, this is like far away from the promised land, but let me tell you some applications of these things. They provide a simple and scalable model, first of all, for us to test algorithms. Second, you can make them as complicated as you like. In fact, they're kind of like, retro kind of arcade games. You can sort of add, doors and buttons and punishments and, dare I say, drop bears. To anyone not in the Australian audience, this is a sort of meme of Australians. You should be really careful of drop bears if you come to Australia. And you can also make these things eventually, I think, applicable to real-world situations such as swarm and group behaviour, emergent behaviour, navigation. I mean, you could also think of just, how do you get your Amazon stuff from, the warehouse to the customer. Obviously, you have a floor of people mixed with robots, or eventually maybe only robots. How do they all work together? And finally, too, this is like a formal setting for specifying cognition, navigation, and for studying the safety problems that can arise, which is mostly what we're talking about today. And in particular, we're going to use a framework called reconfigurable systems, which is due to Abrams, Ghrist, and Peterson, to study these grid worlds. So informally, we have a graph G, we have a set of labels A, and we have a set of states which are a function from the vertex set to our labels. And then we have a set of generators which locally relabel these states. And I'm going to go through this a little bit more formally, but let me first give an example. So this is a 1x5 grid world, and each of these sort of pictures represents a particular state, a particular labeling of the grid world. And what is G? Well, it's a dual graph of the grid world where we put like a vertex on each of these cells, and then we draw an edge if two cells are sort of like glued together, and then we label the vertices with this set A, either agent, object, or floor. So floor is like these empty cells, and if agent is the koala, and ball object is this ball. And then we have two generators here. Push-pull, which is labeled as an orange edge in this picture, and all subsequent pictures, and move, which is colored with this maroon set of edge. And these are the local relabelings. So if you see this set of labels, like koala ball floor, or floor koala ball, you can switch those labelings, so you can just go in either direction. And likewise for move, if you just see a koala and then floor, or floor koala, which is just the same thing, you can switch the positions. And so if you start in this state on the left, which is koala ball, floor, 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 you can the only generator that can be applied here that matches some subset of the graph is this push-pull generator, and then the only thing that we can do, since we're at this state, we can switch to this state. So we relabel, and then we have a new state. And from this state, well, we could just go back again, or we could go forwards, or the koala could go back. If the koala goes back, koala can only go back one, and then it's the only new thing that you can do from here, or the next state that you can get from there is actually just to move the koala forward again towards the ball, and then you're back here. And as you can see, basically every time that you push the ball forward, you gain like an extra step to go back, and so this sort of staircase structure arises. And if I put an extra cell at the end here, then what's going to happen is you can move forward one more, and then you'll have another sort of series of like this many steps plus one that you can go back. So are there any questions up until this point about just like maybe what grid worlds are, or the intuition that we're sort of getting from these state graphs? This is a state graph of them. Is there any question at this point?
Yeah, I guess I'm familiar with Gridworlds in RL, where you would phrase these as actions and then changing the state of the environment or whatever. Is there? I mean, this is just to emphasize like the symmetries or something. What's the?
Yeah. Well, yeah. As we'll see, we're going to lift this to a state complex. So I'll explain what that is in a moment. But yeah, so far, I guess this is basically exactly like the sort of idea that we have in reinforcement learning contexts, but just in a different formal language.
So I could probably translate much of what you're going to say into a more general context just by seeing the complexes inside state space or something, and you're giving me some particular way of just looking at a piece of that information that's more amenable to formalization with the kind of tools you're going to talk about. Is that kind of...
Yeah. I think that's fair enough. Yeah. So just let me like lay out a little bit more formally about what we've done then, and sort of what we can do from here. So a generator phi comprises of the following. We have a subgraph of the graph, and this we call the support, and then we have a subgraph of this, which is the trace. And the trace is what changes. The support is kind of like what needs to be there in order to make a change. And in our case, actually, the trace and the support are exactly identical. Like if we go back here, the support for push-pull is this subgraph, but it's also the trace because it's the things that we relabel. And so a pair of unordered states, you can write like this. They agree on the support, but they disagree on the trace. And they disagree on everything that's sort of in the support that's not in the trace, but they disagree on the trace more precisely. And we say that a generator phi is admissible at some state if we're in one of these local states. And if that holds, we can apply phi to that state and obtain a new state, which is given by this, where we basically relabel all the vertices in the trace set of the vertices in the trace subgraph, and then leave everything else the same. So this is basically just like what we did here. We just looked in some local region and relabeled only that. Okay, and so now you get some sort of interesting structure and symmetry. Is this is a state graph of a 3x3 grid world. Each one of these dots is a state, and I'm showing the state here on the right in this animation, rather than sort of squish this into each of those dots. And then the colors are the same as you saw before. The orange are the push-pull, and the maroon are move. And you get this kind of beautiful kind of flower petal structure. And what I'm going to do is I'm just going to pause this and rotate and add some sort of circles roughly around the collections of states, and just talk about some of the symmetries here. What's interesting is that based on these symmetries, you're able to identify what every state is just by knowing one state. So I give you the information that we're at this state, colored black or shaded darker, and this is the state that you're at. And I sort of challenge you maybe to think for a moment, what are some of the symmetries, and what might I know about, for example, let's say this state here that I'm hovering my cursor over. Notice, for example, these circles indicate actually groups of states where the edges between all the states are all colored maroons. Those are all moves. That means there's no push or pull involved. So actually this means, for example, each of these circles contains states where the object is static, but the koala is moving around the ball. So that's the first thing to notice. But
I don't understand.
Tell me
why.
Sorry. Yeah.
Oh, I see. Yeah, I was thinking you were in this. I was a bit confused about the fact that there was this move one with. So the one in the top right would be the one down and to the right from the black dot. Is that right? Because I have a one move option, which is back to where I was. Yeah.
Yeah. Actually, no, that should be the top. That should right, I believe.
No, that's the position of the beach ball, isn't it? The cluster.
Yeah, that's right. Yeah. So these are the positions of the beach ball, and they're actually aligned to this grid. So this is the top right position for like the beach ball being in the top right.
Yeah, so to understand correctly, if I took the black dot and went up to there, that would be moving down, right?
Oh, yes, sorry, if that's what you said, yes, that's correct, yeah. Because that's the only way I could get to being adjacent to like being able to pull the object into the center.
Right.
And then once I'm in the center, then, okay, this is me like walking around the ball. And then all these things are like me. It's basically there are 8 states in each of these clusters, which is like the space left to move around after the ball occupies one of the states in these 9 squares. So this is quite nice in the sense that by recognizing these symmetries that exist, we've actually been able to interpret a whole bunch of information about the sort of the structure of what's possible to do, and indeed we could cut this up and just sort of explore or notice these symmetries, and we could, for example, cut this. Didn't do a good job there, but we could sort of make some cuts here, and we could potentially just copy and paste this segment and place it everywhere else, and so we wouldn't have to explore the whole environment to know exactly what everything is and how to get to different places in the environment or in the state space. So these reconfigurable systems generate, as we've seen, these state graphs. And so a reconfigurable system in totality has a graph, a set of labels, and generators that work to change those states, and we say that these are together with a set of states closed under the action of all admissible generators at all states. And the state graph, or the transition graph, which will be denoted S1, is associated to the reconfigurable system, has the vertices as all the states, and the edges connecting those states, which differ by a single generator, as we've seen. Okay, so this is state graphs. This is a state complex. And you'll notice here there are some sort of red-ish, pinkish shadings here. These indicate squares, and it may not look like a square to you because you may be more familiar with this square, which is obviously not also a perfect square. But topologically speaking, it is, because we sort of have like this structure here, and then also on the other side. Just going to erase that because it's a little bit, oh, no, I don't want to highlight it because I'm quite proud of these pictures and I don't want to destroy them with these lines. So here we have different states again, which are these different vertices, and then we're connected by edges, which are the moves. And then we have these squares. So the squares are indicating commuting moves. And what I mean by that is that two generators can happen at the same time without really interfering with each other. So notice if we go from this top state to the leftmost state, what happened was the right koala moved up, and then if we go down, the left koala moved down, and then if we move to this state here in the sort of left center, what happened was the right koala moved down. Is that correct? Yep. And then when we moved here, the left koala moved up. So actually, both of these koalas are sort of moving, sort of sliding past each other on the vertical axis. And so that means this square being here means that we can do both of these generators at the same time. They don't interfere with each other, they commute. And therefore it's possible to do both at the same time and sort of go directly past each other without blocking each other. And the same is true on the right side, except now we are doing it horizontally. What happens in this center cycle, for example? Well, here the right koala moves down, the left koala moves up. Then something interesting happens. The right koala moves up. Here the right koala moves to the left, so now they're both sort of on one side. And then here the koala in the bottom left, this one, moves to the bottom right. So actually what's happened, we've done like a half twist of these koalas, and if two full turns will be like a full twist. And all other full cycles that you can imagine, so like if we go 1, 2, 3, 4, are also involving some sort of topologically non-trivial twisting or braiding of the agents, and therefore we don't put any squares there. So these squares indicate commuting moves. And just to make this a bit more formal, a commuting move, or one of these squares we put in, is we see some number of admissible generators in this at some state that can commute when they can be applied independently and without affecting one another. And so it also doesn't matter about the order which they're applied, for example.
Do you mean that if you apply all of them, then it doesn't matter which permutation you used? So it's not that you can't choose to leave some out, right?
That's true. Well, yeah, I mean, you could choose to leave some of them out, but then that would be like potentially a different, like, as we'll see, you could have like a square or a cube or like an n cube, and then if you leave some of them out, then you go from like a cube to a square, for example. So if we have like let's say we have 3 different possible admissible generators. Here we just have 2 and we get a square, but if we had a third one and that let us do like a cube, so that we could go from one corner of the cube to the other corner of the cube without without bumping into each other, then that's like a set of possible admissible generators. But if we drop one of those, then we fall back to the square. And in the complex, all these things exist at the same time. So
I'm a bit confused, because isn't it possible that you're stating it locally at a state, but isn't it possible I apply one of the generators and that gets me into a configuration to which some of the generators do not apply? Like if you had red and yellow edges, for example, I apply a red edge and then there's no yellow edge like there was in your earlier.
Yeah, I see. Well, in that case, if the yellow edge doesn't connect the first state to the second, then that won't sort of be part of the cube, the n cube that we sort of glue onto those vertices, and then that won't be part of this set of admissible generators.
Okay.
Yeah. So a set of admissible generators are the ones that sort of link up. Actually, wait. Maybe I should draw a picture, or is it possible for you to draw a picture?
Yeah, I don't have my iPad in Discord.
Okay. Yeah. Okay, yeah, maybe we could come back to that, because I think actually what I said might be not quite correct. But hopefully in the following it'll make more sense. So a state complex is where we identify these higher dimensional sort of commuting moves in the reconfigurable system at some particular states, and we add in the n cubes whenever there's a set of 2n states related by a set of n admissible commuting generators. So here's an example in the center of a state complex where we've got the same we've got moves and we've got vertices, and this darkly shaded vertex is the current state that we're in. And the sort of red shading is indicating different squares or cubes which are in this behemoth. And you might ask, well, this is the state we're in. Which picture is it, the left or the right? The answer is both, because actually these two grid worlds have exactly the same state complex. And the reason you can see that is because you just invert the labels. Here, change the koalas to floors, and here change the floors to koalas, and you have the same underlying sort of braiding and geometry and topology that's going on. So this is another advantage of this system, is you can identify actually when two different systems are the same dynamically. Now, I've mentioned some cube stuff. It turns out these state complexes are always cube complexes, and I just want to briefly touch on what is a cube complex. So it's like a simplicial complex, if you've heard of those. We have sets of points and lines and squares and n cubes where each face is an elementary cube in X, which is the cube complex. From X, and is also in X. And then the non-empty intersections are also faces. So, for example, this edge here is a face, right? It's a line. It's in this cube complex, and it's also part of these two squares, right? It's one of the edges that are on the side of that, and we're sort of gluing them all together in this case. And then maybe here you have a cube, for example. And all of these are also cube complexes, but we sort of, for convenience in visualization, we don't always draw them quite as neatly as you might like to think of the ideal cube or square or something. So another thing to say is that state complexes are actually non-positively curved cube complexes. So this is a result due to Abrams, Ghrist Peterson, and they have a theorem which says that any state complex of any locally finite reconfigurable system is non-positively curved. And the significance of this is that, and we call this NPC for short, and the significance of this is that you have some very fast algorithms which have been made for calculating shortest paths within cube complexes. So if we want to go from this state to this state here in a grid world, well, if we've already got the cube complex, we know, and this is just the state complex, we know it's just going from this vertex to this vertex, and calculating the shortest path is something that we might be interested in. And it turns out you can do this through basically the very nice hyperplane structure that arises in these non-positively curved cube complexes. And these hyperplanes are basically, cutting the edges along different planes, and then by knowing at the hyperplanes that are around you at any point, just locally at some state, you basically have a list of these hyperplanes that you need to cross, and you're guaranteed that you only need to cross them once. So you'll just have a list of the hyperplanes you need to cross in order to get from your current state to some goal state. And then as you cross one that's available to you, you're guaranteed that you won't have to cross it again. And you'll also be guaranteed that whatever state you go into next, there'll be at least one more available hyperplane that you need to cross. And this is a sort of summary of a paper by Ardila et al. In SciAm Applied Math in, I think, 2007, and it's in the references of the preprint we have. Now, how do we know a cube complex is actually non-positively curved? Well, we use something called Gromov's link condition. Well, there are other ways, but this is a way of explicitly testing it. And I want to just give an intuition as to what we're doing. So here we have two cubes. One is a solid block of cheese and the other is a hollow box. And if we cut on a diagonal one of these corners, or in both cases, the solid block of cheese, its cross-section will sort of look full, right? And it's kind of like a triangle with full interior. Whereas the hollow box will have like empty space in here. It'll just be a sort of triangle without any with anything filling it in the middle. And you might notice, or you might suspect, that this might lead us to something about simplicial complexes, and indeed it does. So Gromov's link condition is the statement that, or the test to see for any finite dimensional cube complex, it's non-positively curved if and only if the link of every vertex, which we denote like this, is a flag simplicial complex. So this isn't a simplicial complex where these are vertices, these are edges, or one simplices, and this is a two simplex or a triangle filling in the middle. So this is a flag simplicial complex because, I'll explain. A flag simplicial complex is one where we basically don't have any holes, everything is filled in. So if we have the boundary of some simplex, we must have the simplex which that bounds. So a simplicial complex is kind of analogous to a cube complex, if you hadn't heard of them already. And instead of having n cubes, we have these n simplices, which are generalizations of triangles. And a simplicial complex is flagged when there are so-called no missing simplices. So let's do some examples. On the left, this is a cube complex, and on the right, this is the link of this vertex. And the cut, quote unquote, that we're sort of making, kind of analogous to that, like diagonal cut through the corner of the block of cheese or the cardboard box, is in this local vicinity here. So this little red sphere or circle is local to this vertex, and we're sort of cutting around there and making our cuts there. So then each of these lines is where we put a vertex. So if I can maybe draw in, let's say, this color, here we put some vertices, and then because there are cubes which are sort of indicating in our system commuting sets of these things, then we put edges here, and then we get this picture on the right, and we don't fill in anything because there's no higher thing. And then what this indicates, since this is a flag simplicial complex, since there's no edge going like this that would bound a triangle, then this is a flag simplicial complex, and therefore we have non-positive curvature, and in this case it's null curvature. Okay, here's an example of negative curvature. And hopefully you can see that this is pretty similar. We just put some vertices here and then draw the edges there, and you get this picture. Okay, and then here's an example of positive curvature, and you get that through this picture. And what do you know? We don't have like another. Maybe I should do this in another color. Let's make it in green to stand out. So if I had some vertex out here, and then also that this was all filled in as a cube, then I would have this triangle filled in, but I don't. And the triangle would be filled in because then I would, and in our case, I would have kind of like more computing moves. So in these little links, basically the vertices are admissible generators, and the simplices are the commuting generators. And here it's like we don't have an extra dimension to go up to, and therefore we have this missing simplex, and therefore we have positive curvature. Now, but why am I going through all this? You'll probably discover a little bit later. But just so far, you can just know that this is how we test non-positive curvature in a cube complex. All right, so it was a lot of explanation. Why? And here's the reason. We actually create a new type of cube complex, a modified cube complex, a modified state complex, rather. And it arises from this observation. Well, if you have a 2x2 grid world with one agent, and you notice the agent is like walking around in a circle like this, there's a hole, topologically speaking, in this cube complex, right? There's no square here. And yet, it feels like there should be. And this feeling, on the basis of this feeling, we put in the square. And so the feeling really is like, well, it shouldn't matter. It shouldn't matter, right? If I'm at the bottom left, it shouldn't matter if I go up and then right, or right and then up. Like, those two things commute in terms of their order. Of course, the koala can't exactly go up and right at the same time, which might be implied by this square, but it's sort of the only reason this is occurring is because of our discretization of the plane, which we do at the level of the formalization of a grid world, right? Like, there's no sort of blockage, right, between this koala moving in any direction. It's just the fact that we discretize it on the plane in the form of the graph that we get these holes.
Isn't it more like an artifact of the fact that you have one generator called move rather than move up and move right?
Yeah, also, right. So actually we've also been thinking about, we could also fix this by just modifying the generators. But at least for now, we thought, at this stage, how about we just add in the squares where we see this situation? And we call these squares a dance, a 4-step dance. So, in fact, we call these like Dancing with Myself, which is a reference to like an 80s song. And we denote these delta. They comprise the following data. So we see a support like you saw in that previous picture. And we have 4 equals states, which each have exactly one agent label and 3 4 labels. And then move generators sort of transitioning between them. And we say that this is admissible if we're at one of those local states. And then we define our modified state complex, S prime, of a grid world. And we obtain this by filling in, starting with the state graph, doing the regular sort of squares and n cubes for all those commuting moves. And then we also add the dances. And specifically, we get this larger set of stuff because we're adding things. And then, what happens to this example? Well, nothing changes because actually there's no room for these koalas to be dancing. So we preserve that interesting topology. But then we get situations like this. So we get situations where Gromov's link condition can fail. And here I've sort of illustrated 2 examples where we're at a particular state, and I've sort of drawn in the different generators that exist, and the links are down here. So on the left, we have these two koalas in this little situation here. We have phi 1, 2, and 3. These are different moves, so these are different vertices in our link, and those are linked up here by these edges, because 1 and 3 can happen at the same time, and 2 and 3 can happen at the same time. And then in a sense, our dance lets 1 and 2 happen at the same time, in some sense. But what this causes is a non-flag simplicial complex. So this means that we have positive curvature. And here we have two dances that are sort of colliding on the diagonal, and in this case we have like a void in the center of this tetrahedron. So this is not a filled-in tetrahedron. And it turns out that those two examples are exactly the cases where Gromov's link condition fails, and we prove that in our modified state complex of agent-only grid worlds, the link satisfies the link of any state satisfies Gromov's link condition only if it has no 2 or 3 simplices. So if you've checked those two levels, you don't have to worry about anything higher. And also it arises when you have a pair of agents whose positions differ by either a knight move from chess or a 2-step bishop move. So this is like a knight move in chess, if you're familiar with chess, and this is a 2-step bishop move. So that's pretty interesting. So we completely characterize the positive curvature, even though this arises and this, is kind of detrimental to using efficient algorithms and whatnot.
So does the second condition mean that it's possible for the two agents to get into a position that differs by a knight move or 2-step bishop move? I mean, they may not start there, but...
well, yeah. So obviously there are cases that this won't happen. So like this case, for example, you have two agents in a small enough room that they just can't be separated by a 2-step bishop move or a knight move. So it sort of depends on the shape of your room, basically.
But am I correct in thinking that basically this is most of the time true for most of the grid worlds you would write down? Yeah.
Yeah, exactly. Yeah. But what's interesting is we can sort of interpret this as sort of identifying moments or states where the agents could potentially collide, right? So this is like two dances colliding or a dance colliding with a move. Now, if you just remove the dances, then of course these collisions don't happen. And also, if you modify the generators, then this also doesn't happen. But I suppose what we're sort of highlighting is a way of thinking about these discrete navigation problems as sort of in this geometric way, and then using some geometric information to identify those states where you could potentially have some collisions or danger. So it's kind of like a danger detection algorithm, or way of thinking at least. I don't think it's a very efficient algorithm for detecting danger. Although by this second condition, you don't have to actually construct any of the links or do anything. You can just look at, do two agents differ by a knight move or a 2-step bishop move. So you see, in general, for example, in this case, there's without even looking at any of the structures, you can just see the positions of the agents are differed by a knight move here, a knight move here, and you're going to have failure conditions there. And then also if they swap sort of if they flip on the vertical axis, then you're going to have another 2 knight moves there. So there are 4 failures in the link conditions that break the link condition. And this is the state complex here, with the blue shaded squares being the dances and the red shaded squares being the sort of commuting moves. And this is an example of a 3x3 grid world, and indeed you see a lot of failure like there. And of course, across this diagonal, you'll get cases where they're in both corners. So yeah, there's a lot of failure that can crop up.
I'm sort of interested in the way you're presenting this, which I guess is an insight into the state of the literature. If I just query that a bit. So, I mean, if I think about the variants of Gridworlds I've trained RL agents in, I imagine that basically, I mean, I was trying to, like many people interested in problem solving or some other kind of capability of an agent in a grid world, and almost all of the interesting features of the environment probably generate situations like this, right? I mean, a sort of non-commutativity is basically, I mean, if you think about someone designing a puzzle, this is exactly what they're looking for in order to actually make it difficult.
Yeah.
So you say failure, and that's just like a reflection on the existing literature kind of focusing a lot on this NPC condition, or is it?
Yeah. So people in geometric group theory and people who study cube complexes really want their thing to be non-positively curved, because it gives access to this wealth of, stuff, including algorithms, which are useful, but also properties which are beautiful or nice.
I guess my first reaction to that would be it's the looking under the light pole effect. Why do I think this is like actually something that in nature is relevant? Surely most environments are failing this like almost always or something.
Yeah, exactly. And I mean, indeed, in nature, we always have these, situations where we can potentially be bumping into each other, right? And so this failure condition is sort of, we're trying to show a positive, a positive benefit of looking at for this thing, rather than trying to prove that it doesn't exist.
Mm-hmm.
In sort of from the mathematical perspective, I guess that's one outcome. But the other outcome is to sort of show the AI and Neuro people that, look, and I suppose we'll get into more of the Neuro stuff in a moment, is to say, well, look, some of these tools, while sufficiently abstract and not really close to how nature works in our continuous, seemingly continuous kind of spaces, we can maybe still find some new perspectives, basically from a formal perspective like this and a geometric perspective, which could let us use some of the algorithms or some of the properties of those structures to discover something about, or a new way to discover something about, let's say, danger or navigation in multi-agent systems.
Mm-hmm.
So we also did a little bit of data collection in the form of, like, we did simulations of, or we didn't do simulations, but rather we sort of just like constructed the modified cube complexes of situations with different numbers of agents in a 3x3 grid world, and then calculated, like, of course, what are the number of states which are non-positively curved, like their percentage, and also how many dances there are, how many commuting moves there are. The commuting moves the same, about 4.5 agents in each direction, and that you kind of already knew. Interestingly, the dancers also do the same thing, about 3.5 agents, and the reason why this is kind of shifted downward is because if you have sort of too many people on the dance floor, you can't dance. And then here we also just look at the total number of these failures. So you can interpret these failures as instances where two agents are sufficiently close to each other they could sort of accidentally bump into each other, at least under the set of generators that we started with. And the maximum number of failures per vertex, on like a per vertex basis, and the total number of failures, and then the average across, like what per vertex, how many, since each of these have different numbers of states. And what are some applications? Well, first of all, we can use this positive curvature to indicate a situation which can potentially be unsafe. And our theorem can also be interpreted as a way to say that, well, we need only a bounded amount of foresight to detect potential collisions. So you can also think of this kind of like in some computer games, there's like this fog of war where you don't see around a corner, or you don't see far into the distance, so you can't see the other agents necessarily, and that can happen, of course, in real life, like when you're walking around a corner. But here we're saying, since you only need to check the 2 and 3 simplices and you don't have to worry about anything further, it's also the case that you don't have to look around all corners. You just have to look around, like, for example, the next corner, and we sort of have a way of describing that a little bit more precisely and formally. And this we think may help some safety navigation research to prevent collision or provide coordination, and further geometric and topological information, could be used to improve learning algorithms in these kind of environments. So maybe I just pause here in case anyone wants to discuss these things, and before I go on to start heading towards more of a neuroscience direction.
Yeah, maybe that's what will answer my question, but I don't get the impression that these are the things you care about. So what drew you to this? Where did this idea come from? Why did you start caring about this?
I cared about this maybe purely just out of interest in the math, but also like the geometry and topology. So I suppose, yeah, probably that question will be answered in the following.
Yeah.
In the following material. Yeah.
But I guess there's a few ways you could see this as almost having nothing to do with neuroscience, right? It's just you have robots in the environment, and you're trying to do planning and blah blah blah.
Yeah. Right.
And that has a lot of overlap with maybe trying to understand how existing agents, biological agents, do planning in an environment, and I'm guessing it's that's more your inspiration, right?
Yeah. Exactly. Yeah.
Okay.
And in particular, I'm sort of maybe just to preface what follows. I'm sort of interested in okay, this is one way of potentially identifying collisions or doing collision avoidance, and also thinking about the environment and symmetries and so on. Does any of that map to the way natural learning systems operate, or not?
Mm-hmm.
Yeah.
My students are also afraid of non-abelian groups.
Okay.
Danger.
Yeah. I thought that this was a pretty, like, just from the mathematical side, I was kind of interested in this too, I have to say. Yeah. Also, I guess, I think you mentioned something on Discord about braiding. So another question we have about this from a mathematical perspective is like, is the n-strand braid group like is this a classifying space for the n-strand braid group? Since really, like, if you just connect like a ribbon or a string to each of these agents, like looking from the top down, with our modification, you sort of can get all the possible braids, we think. Yeah, but anyway. We have to think more about that. I mean, it seems like that should be true, but we're yet to prove it. All right, so let's move a little bit more towards the promised land. So predicting grid-world dynamics. Let's imagine that we have a little mini feed-forward neural network, and we give it a state, and we ask it to predict the next state in the grid world. In this case, under our sort of generators from before, there's three moves that can happen, and so the koala could end up in these three positions. The ball won't change position. So we're expecting this outcome, and we train a network to do this very simple task. And then what we do is we look at the hidden activations in this neural network. So here are 50 neurons in this particular layer, so it's 50 dimensional. And then just for our sake, we do some dimensionality reduction in what we'll present today down to 2 dimensions, and we use PCA. So why is this interesting to do? Well, consider a similar network, a multi-layer perceptron, which is trained to identify MNIST digits. These are these handwritten digits. So we have an input layer, 2 hidden layers, and then an output layer with 10 different outputs, which will be so-called one-hot vectors. That is like a 1 in the position 8 of the vector if this is meant to be an 8, and then 0s everywhere else. So that's the sort of ideal. And then again, we'll look at the dimensionality reduction of the hidden activities here. So once we give an 8 and we push it through the network after it's trained, these activations should have some structure to them if it's learnt something interesting. And here is that structure in two-dimensional PC space, principal component space. And I've colored the different points here according to when we fed through a different number, the color is different. And so 8, for example, is here in the middle. And I think this is kind of making sense from a combinatorial point of view, since if you consider liquid crystal displays, when the number 8 shows up, it's actually displaying all possible areas, like all possible segments of the other numbers. It's kind of like it's this sort of geometrically speaking is kind of like, okay, we're here in the center, we've got everything, and then we're sort of doing some minus operation. We're getting rid of stuff when we move out away from the other to get to the other numbers. And you notice, for example, let's see, this green one is number 2. So yeah, it kind of makes sense that's away. But then what about this pink one? Let's say the pink one is 6. Okay, so that's going in that direction. And you can sort of look at these from the perspective and do different dimensionality reductions. But this I think makes sense that 8 is in the middle. That's my claim anyway. Does anyone disagree?
Sure, why not?
Okay.
I don't know about the story you were starting to tell with directions or whatever, but
okay, yeah. Well, I suppose the story I'm sort of about to tell or trying to say is that it makes sense to think about, like, in this kind of underlying manifold of the representation space that it has to develop in order to sort of shift our points from this high dimensional space eventually down to this low dimensional space of just the classifications. In order for that to happen, we need to sort of like separate the classes, right? And so it makes sense that somewhere along this chain that we'll get a separation of those classes, but in order to handle so many different data points and so many new different data points, we have to sort of do it in a way which maybe makes some algebraic or logical sense. And in this case, in this example, I think that based on this kind of argument, 8 should go in the middle if you were to design this. Yeah. So for the grid worlds, what should be something, what could happen there, or what should happen there? I didn't actually have a good intuition, but here's actually what happens in the simplest toy example I could think of, which is just a 3x3 grid world and a single agent. So this is, laughably simple for
So just to be clear, there's no reward here or anything. You're just asking it to predict the possible next states, sort of the connectivity of this graph.
Yeah, exactly. Yeah. And so from this state, there are 3 possible states. And if I give if I give basically this in a vector form, it's like a 1 hot vector with a position of like a 1 where the agent is, and 0s in other spots, and I'm asking, like, where's the next 1? But as I do that, it's obviously going to interpret where are we, what is the vector representation that we have now, and put that in this PCA space. So there are 9 different points here, and these different points represent the hidden activities in 2 dimensions from the 50 in the same network as shown before. And what I can do is I can circle, just ignore these lines for a moment, I can circle this particular state, so that's, I think, this one up here, and then I can just, when I get the output, put that output, feed it back into the front end of the network as an input, and then see what are the subsequent states that I go to, and it turns out it's these 3. So
sorry, actually, I'm a bit confused again. So actually, rather than MNIST outputting a single class, if it's correct, this is outputting a distribution over the possible states, right? So how am I thinking about that? So
so it's kind of like if I so like the input will be 0, 1, 0, 0, 0, blah blah blah, and then we go through the neural network, and then the output will be something like 1 over 3, 1 over 3, well, 0, 1 over 3, something like this. There'll be 3 elements in this case, which are a third, and everything else will be 0. And these 3 things here are the ones
that's
that we
the solid
identified.
versus open circles. Okay, I got it.
Yep. And so we go through this process for all of the other vertices, and that's how you get these lines.
Sorry, I'm not understanding again. So you're taking the activations from like some part of the network, maybe it's exactly the same network, but then when you do the PCA, I mean, why is it 3 separate dots? Isn't this 1/3, 1/3? I mean, the hidden activation that's going to predict that should just be a single dot here, isn't it? When you do the dimension reduction, and why am I?
Yeah. So these single dots are the these single dots are when I give this state, and I put it through the neural network. I stop. Well, I look at the hidden activation somewhere in the middle here, and I do my PCA. And if I do my PCA on all possible 9 states, I have these 9 dots.
Okay.
And then the next step to sort of like relate these dots to each other is I look at the outputs after I put each of these dots through the rest of the network, and then I ask, okay, these are the states now, these 3 that you're pointing to next. And then I ask, okay, where are those in the PCA space?
Okay, so the dots are sort of like encodings of these states if you read off these.
Yeah, and then but now I want to understand, okay, how can I relate these in a graph structure? So I do that through this process, and then I get this is the full sort of like graph. And because it's a graph, well, we can just, for example, like label the vertices and sort of rearrange them. And it turns out, of course, to be a dual. Yeah.
Sorry, how did you get these lines between the letters here? Sorry, I think I might have missed that.
Yeah. So once we put through the state to the end of the network, we see what are the predictions. So the predictions correctly are a third in each of these different states, for example, and then we look, since this vector is the same size and sort of has the same order as the input vector, we look where are those in this input vector, and then we set one of those, like we do that 3 separate times where we replace a third with 1, and then everything else 0, and then 1, everything else 0, 1, everything else 0. And then on each occasion that we do that, we look again at the internal representations for those 3 different positions. And so then on that basis, we can identify, okay, if we're in like this open circle identified state, where are the 3 states that you point to?
And then you just like do that for all of them.
Do that for all of them, exactly. Yeah.
Cool, thank you.
No problem. Yeah. And so, importantly, we're not kind of like using information. I believe we're not using information external to the network in this by doing this process. I tried pretty hard to make sure that wasn't the case, since it feels very easy to cheat. But if other people have different ideas on how to do that even more rigorously or more confidently, then please let me know. So since it's a graph, we can sort of rearrange the vertices if we want, just for our own visualization. And it turns out, of course, you get a dual of this grid world, which is expected. But what's interesting further is that the positions in this space, in this low-dimensional PC space, actually has some patterns to it. So, for example, the sides, seen here in yellow, are all on the right side of this picture in the PC space, and the corners in the middle are all on the left. And also too, if you look at sort of local pairs, so for example H and G, H is ever so slightly above G in this picture, and so it's got a slightly larger PC2 component. And H is also above G in this drawing that I've made sort of in this Cartesian system. So then also B and C has the same thing, D and I, A and E. F doesn't work, but A and F works, but the pair F and E doesn't work. E is a bit of a special case because it's in the center, I think. So to me, it seems like we have some internal representations which correspond to, for example, like the graphical structure of that sort of underlies these dynamics, which of course I think kind of makes sense. And ongoing work is to discover or to test high dimensional sort of generators like dances or committing moves also generated. But we haven't done that yet. Now to sort of throw a really different piece of information into the fire is some neuroscience about social place cells in rats and bats. So you might have heard in different animals they've identified something called place cells. These are cells where if you're in a position, it's said that this particular cell or a particular class of cells, one of which will identify you as being in this place in the environment. But there are these other cells which not only act as self-place cells, like where I am, but also where my conspecific, my fellow species member, is also in the environment. And these are called social place cells. So take, for example, this section on the right, on the left is for the rats, and section on the right is for the bats. So we'll do the rats first on the left. So panel A shows two colors of rats. One is orange and one is blue. And these blue sort of lines are different ways that the blue rat is running. And in B, we have the same thing for orange. The orange rat is running. Now, the blue rat is always told, sort of trained to go to the left, and this place cell, this social place cell, is being recorded always in the orange rat, and the same color code goes for the bats. So while this orange rat is looking at the blue rat, it's got a place cell, a social place cell, which is becoming active where these little red dots are happening. And if you do a coarse kind of heat map, it's in these two locations here. So when the blue rat is in this location or this location while it's running around, and it's taught to go that way, it sometimes goes that way, but never mind. So when it's got these, when it's doing these trials, this cell in the mind of the brain of the orange rat is firing at these locations. Whereas
when you say firing at those locations, just to clarify that this isn't like a relative position thing. It's that cell is somehow associated to, in some way that maybe you won't explain, but somehow we know it's associated to this like objective, absolute coordinate relative to the maze, right?
Right. You've almost revealed my hypothesis. So
sorry.
So they do. Yeah. So actually, no, don't be sorry. So yeah, that's exactly the question, right? So in this case, they fix the location of this orange rat, right? They want to eliminate too many variables because they're experimentalists and they want to control things, and that totally is sensible to do. But the consequence is that I think a question arises, which is, is it absolute or is it a relative position? I think it's a relative position in coding. So you'll notice for the self-coding, it's in this location, right? Which happens to be where it was making the observations from. It also happens to be, in a sense, kind of like the location that you might care about. Like it's kind of looking around the corners or looking like one or two steps ahead. So maybe vaguely, something about collision avoidance could be said, or at least coordination. It's caring about positions which are close to you, basically.
I think I'm not following these two diagrams. I'm sorry. So,
okay.
In the first one,
A.
Yeah, there's sort of like a time dimension here that's not shown or something. So when is the reds? I mean, the firing heat map on the right. When is this? It's firing just like before the blue rat moves, but then like what's the relevance of it going to the left? I don't really understand.
That's just I suppose an extra variable that they want to note, but it's not actually. So that arrow is indicating where the blue rat was trained to go. It was trained to go to the left, and the orange one was trained to go to the right.
Okay, so this is somehow like the paper you're referring to does a bunch of things. You don't care about some of them. You're telling us this.
Yeah, we don't.
Yeah, so you don't care about the going to the left. You're just sort of interested in the fact that it has this social place cell.
Yeah, exactly. Yeah. Okay. And the heat map is sort of like time independent. So this is just like not caring about time. This is just overall time. These are the places in the environment that are being fired at the most. But it's a very coarse kind of graining. Like you can see there are a few rogue spikes activations up here which are not sort of showing up on this heat map. Likewise, these things are showing up here. But I suppose it is slightly there, but none there.
Cool.
Yeah. So that's the rat. The bat is a similar story, and again, ourselves, like the one that's sort of observing the other, is the orange one, and we're moving or we're watching bats go in this direction always. So this is kind of at least not including this variable of like left or right. But interestingly, again, we have the case that the other encoding is kind of like a little bit forward in time of like where we would go in the future, and our self-coding is like not only where we observed, but also where we actually no. In this case, sorry, it's not where we observed from. This is they sort of put it, I think, here, like maybe not exactly there, but rather kind of like here, so that it can look both ways.
I see. So this is the same cell in both cases, or what? I don't really understand.
Yeah. This is the same. So they will previous experiments would have identified this as a single place cell, but these papers here have sort of identified that not only are some of these place cells encoding for where the individual is, they're also encoding for where other individuals are, and therefore they rename this place cell as being something that encodes jointly for my place but also others' place, and they call that a social place cell. So these are, in both of these examples, we're talking about the activity of a single cell, the same cell in both cases.
Not confusing at all. I find this rather hard to follow, but okay.
Yeah. So maybe just to say it in slightly different language and use some pictures. So we have some area of hippocampus. We identify a place cell. Let's call that place cell. And previously, people would have not looked at the blue. They would have not looked at this or this. They would have just looked at these bottom rows here, the orange stuff. They would have not this blue thing, character would just not exist in their universe, right?
Mm-hmm.
And they would look at these activities, right? And they would say, okay, this is a place cell that encodes for this place and this place, right? And now someone else said, oh, but I want to study multiple agents in an environment, and then they added in the other agents, and then in the same cell, looking at exactly the same cell, so it's the same place cell, they saw that, well, if I just don't let my animal move but let another animal move nearby,
okay,
it will show up here and here.
Yeah, I think I wasn't quite getting that. The red dots show where the orange. No, they can't. So in B, the red dots show where the orange rat is when this cell fires. Is that right?
Correct. Yes.
And in A, it shows where the blue rat is when that cell fires.
Correct.
Yeah.
Correct.
Okay.
Yes. and same, but for D and E.
Okay, I got it. Yeah.
Yep.
Yeah, that's pretty intriguing.
Yeah, it is pretty cool, right? And to me, the pattern is that the social places are always kind of like ahead in an ecologically kind of sequenced way, ahead or like nearby in an important sort of collision avoidance system potentially, for the self. And so on this basis, I immediately, actually I have some more about this. But actually, how are we going for time? Let me just check.
We have our next seminars at 10:30, so I guess we should wrap up in 10 minutes or so.
Okay, right. Maybe I'll just skip this, but you can do this in more sophisticated ways. So yeah, the hypothesis is that I have is that egocentric vector social place cells. So these extra words I'll explain in a second. Egocentric vector social place cells could be a basis for collision avoidance. So it's got a similar vibe to me, and I know that's not a very precise way of saying it, but it sort of it feels like these place cells, these social place cells, care about where I'm going next, and they care about tracking, where it can, where these other agents are going to be next and where I might be next, and so therefore like where we might both be at the same time. And that I think is an important bit of information to keep a track of. So the vector part is kind of like implying something about, well, it matters which way I'm going and like kind of the sequence that I take. And egocentric, well, obviously this all matters for like the perspective from myself rather than the perspective from another. And there have actually been some studies on this. Probably it's going to be too much to go through all of these, but let's just go through, for example, maybe this set on the left. So these are vector. These are. I think these are vector-based representations of space. So these different colors indicate spikes from different cells. From the same cell, right? But the color is the direction that you're moving in. And so it turns out you care about, if you're one of these cells, so these are sort of like the vector-based cells, if you consider which way you're moving, when you're going towards one of these walls, you go towards it, it fires more and more and more in that when you're going in that particular direction. And so in all these cases, these are 3 different cells, 1, 2, 3. These are these different rows of different cells. Then the direction of movement matters quite a lot. And in a sense, these other example cells in the middle and on the right are exactly the same, but basically further away from different objects, or in these cases, the objects that I'm talking about are the walls of the environment. So these are this looking top down in some environment. And I haven't done this justice, and I may not have time to do it justice.
Do you think?
Yeah.
So, I guess I understand, given the context of a lot of the sort of grid cell research and its emphasis on social relations and so on, there's a reason why it's called a social place cell. But do you think it's more the division between something dynamic in the environment and something static, or is it really something special about another member of my species?
I think it's more about some dynamic thing. So, most of the social place cell work has also kind of been wrapped up in like social behaviour or other sorts of studies, which obviously, have traditionally always been between members of the same species. So, not always, of course, but that's where they've done a lot of lab work. So I think actually it's really just about a dynamic change that's relative in the environment. And indeed, as a big fan of people like Tim Behrens and their work, it makes a lot of sense in that framework. So, yeah. So it might be fair to even say something like ecocentric vector, replace the word social with something else, place cells, or just even get rid of place as well. Egocentric vector dynamic cells, I don't know, something like this.
Yeah, I've seen some speculation along the lines of sort of, maybe they didn't say it exactly this way, but non-trivial topology or higher simplices in connection with, I don't know the exact term, but if you took a grid world and then you cut off one of the doorways or made it inaccessible, right? So you, and then detours, right? There's some like focus on detours, and this is in the successor representation literature. But so I guess it's maybe a little analogous, but here you're talking instead of changing the environment, it's like another agent in the environment that reconfigures the possible actions you can take in each state.
Yeah, exactly. And, like that could have a consequence. Well, I mean, that always has a consequence, I think, in your behavior, right? Like if someone is blocking a doorway, that's kind of the same as if the door is closed, or the like functionally speaking, as if there's no way to go through.
Yeah, but it's a very natural place to look for higher structures in topology or whatever.
Yeah. So, these are the take-home messages. First is that purely geometric and topological features can capture this non-trivial task information, for example, like collision detection, but also, as we were just discussing, things about, like, for example, the functional behavior that I can exhibit in some environment. Such features seem to be learned potentially in learning systems, and this gives a little insight or a little hypothesis for a social place cell, a rethinking of social place cells, basically. So I think that's
thanks, Tom. So there's
future directions. Yeah, more labels, more generators, fill in different cells in the complex, optimization things, braiding. We have our software. It's all available if you want to play with that. So you can create. So I've made this little GUI thing so that you can, create your own grid world and put in agents and objects, and there's other things you can add in, and you're welcome to do that. And then I've also got all the code for you to, make a state complex or modified state complex.
Cool.
Yeah.
So, which do you think? Do you think navigation or social navigation has more difficult, higher dimensional structure? I mean, clearly, giving my wife flowers and then asking her to do me a favor is very different to doing it in the reverse order. But is this right. Are there more examples of this kind of non-commutativity in social interactions than there are in navigation, or are they just sort of feel more or less the same to you?
They feel totally the same. Yeah, I don't actually, even though my thesis title says something like geometry and topology of navigation and memory or something like that, I don't actually think that there's a difference between navigation and memory, or a meaningful difference anyway. So yeah, and what's interesting too, that you sort of analogize there with giving flowers and asking for a favor. Obviously, the reverse doesn't work so easily. Then it's these things also have directionality. Obviously, in what I've shown, there's no directionality except for the social cells, right, in the data that I showed. But
this is actually topologically more complex, right? So this is actually something that happens in like homotopy type theory as well. There's sort of a complexity to do with directedness that is harder to handle sort of natively in topology, which, I mean, simplices.
Yeah.
I mean, there's kind of an order to them, but it's sort of erased most of the time. Yeah, that's interesting.
Yeah. So actually, next week I'll talk a little bit about Karina Curto's and others' work, which talks about simplices, and in that case too, we we are actually thinking about like putting orientation onto these simplices in order to capture some directedness in sort of the connectivity and activity and dynamics of these neurons. But yeah, it makes it much more complicated.
Yeah, it's interesting. Yeah, just for those listening who haven't sort of seen this literature before, there's a very interesting vein or theme of research, which some of which is being mentioned here, which is making analogies between the kind of structures that evolved to deal with navigation in space and the kind of structures, or maybe the same structures that were co-opted to deal with reasoning about social situations. Makes a lot of sense somehow, but it's very fascinating to see it cashed out in the neuroscience literature.
Yeah, indeed. Yeah, and even further, I think just making analogies generally between navigation and almost anything else is kind of fun. I think quite a few people, myself included, think that nervous systems arose mainly to first do navigation towards food, away from predators, that kind of thing. But then was, also found use in sort of analogies to more complicated behavior.
For example, at the end of a seminar, you might say, "Moving on."
Moving on, indeed. Yeah. Thanks very much for your time.
Yeah, thanks, Tom. That was great.